As always, we are AI-generated hosts, which, we've stated since episode 1.
Yeah, the research is human, but these voices are AI.
Exactly. And just as a reminder, the episode description links to a source teardown, separating verified facts from AI extrapolation, so definitely check that out.
For sure. Always good to look at the raw data.
Right. So, 10 episodes, 3 VTT reports, 1 mule bike charging at a Circle K.
Yep.
And then the 4th report landed. And we're looking at 1 contested pouch cell, 3 mutually exclusive hypotheses, and 1 single physical test that could just settle it all.
Yeah, just 1 test.
But, usually when we talk about a diagnostic test, there's this expectation of precision for you as a listener. Like, if you break your arm, right, the X-ray shows a jagged white line.
Yeah, clear as day.
Exactly. The doctor just points to it, the bone is broken or the bone is intact, it's clean, it's binary, and frankly, it's comforting. We like things to be visible and, neatly categorized.
Oh, absolutely. We crave that certainty.
But if you step into a really complex field, like autoimmune disorders or neurodevelopment, suddenly that X-ray machine is just totally useless.
Right, because you're looking at a diagnostic landscape that is entirely murky.
Exactly. And today, I want you to keep that image of the broken X-ray machine in your mind, because we are stepping into a technological diagnostic landscape that is just as fiercely debated.
Yeah, it's a fascinating pivot for this ongoing investigation we've been doing.
It really is. We're going to look at how different, incredibly brilliant minds can look at the exact same data and deduce, completely different physical realities.
Right, because in our previous deep dives, the progression was highly linear.
Very step-by-step.
Yeah, we saw the 11C fast charge verified.
Yeah.
We mapped the CT coding corporate network. We watched the pack level charging demonstrated on that mule bike.
Right, the real-world proof.
But then report 4 forces us to return to the raw science. It doesn't upend the narrative, but it provides one more vital, extreme data point in a very long series.
So the mission for today's deep dive is highly focused. We are looking at a single piece of hardware, a battery designated as cell DL2.
Cell DL2.
And we are dissecting the most scientifically substantive public debate in this entire saga. And I want to set a ground rule for us right now. For you listening, we are not here to declare a winner.
No, the debate is completely open.
Totally open. We're just here to examine the evidence, break down the physical mechanics of these arguments, look at the epistemological asymmetry of the debate.
It's a big one.
Huge.
Yeah.
And identify the physical test that could resolve it all.
And to really understand the debate, we have to understand the object at the center of it, right?
Yeah, let's get into it.
So VTT Report 4, which is officially document VTT-CR 0017-826, it details an event that was never supposed to happen.
Never.
It was a purely reactive test born from an accident.
Right. Let's trace the history of this specific battery, cell DL2, because calling it a survivor feels like a massive understatement.
Oh, yeah. It is the most abused piece of hardware in the entire testing campaign.
By far.
It truly is.
Yeah.
So DL2 had already been subjected to a baseline room temperature capacity test just to, verify its performance.
Standard stuff.
Right. But following that, VTT pushed it into a plus 80 degrees Celsius discharge test.
Okay, 80 degrees Celsius, that's about 176 degrees Fahrenheit.
Which is incredibly hot.
For a standard lithium-ion battery, operating at that temperature is basically a death sentence, right?
Oh, absolutely. The liquid electrolytes begin to break down, pressure builds up, and the degradation is catastrophic.
But DL2 didn't just survive that test, it actually gained capacity, like 10.5% capacity.
Yeah, it gained energy.
I know we touched on this in a previous deep dive, but let's pause and explain the mechanism behind that again, just because it perfectly sets the stage for the chemistry we're looking at.
Yeah, it's crucial. So that capacity increase is a signature of solid-state architecture.
Right, because of how the ions move.
Exactly. In a liquid battery, ions swim through a fluid. Heat might make them swim slightly faster, but mostly it just boils the fluid.
Which is bad.
Very bad. But in a solid-state battery, there is no fluid. The ions are trapped in a rigid ceramic or polymer lattice.
They're stuck.
Right. They don't swim. They have to literally hop from one crystalline site to the next.
Sounds exhausting.
It takes energy. At room temperature, that hopping requires a lot of kinetic energy. But when you apply heat like baking it in an industrial oven at 80 degrees, you add thermal energy to the whole system.
Okay, so the lattice itself vibrates?
Exactly. The lattice vibrates, the carrier ions become highly excited, and their mobility skyrockets.
Oh, wow. So they can hop way easier.
Yes, the internal resistance drops, allowing the battery to access pockets of capacity that were kinetically locked away when it was at room temperature.
That makes perfect sense. Heat loosens up the rigid ceramic maze. So feeling confident after that 80-degree test, VTT pushed DL2 even further. They subjected it to a plus 100 degrees Celsius discharge test.
212 degrees Fahrenheit.
Literally the boiling point of water.
Yep.
And that is where the incident occurred. The pouch cell lost its vacuum.
Let's visualize what that actually means for a second. A pouch cell is essentially a stack of microscopic electrode layers sealed inside an aluminum laminated foil wrapper.
Like a high-tech Pop-Tart wrapper.
Basically.
Yeah.
And to keep all those internal layers pressed tightly together, which is absolutely critical for them to make electrical contact, the manufacturer sucks all the air out before sealing it.
Okay.
So it looks and feels like a tightly vacuum-sealed brick of coffee. It is rigid and taut.
But during the 100-degree test, that tight, sealed package failed.
It did.
VTT reported that the pouch went from being rigid to being loose and wrinkled. The vacuum was just gone.
The outer packaging failed under extreme thermal stress.
Mm-hmm.
Now, in standard battery development, this is where the test ends.
Right, you throw it out.
Exactly. If you're a battery manufacturer, you do not pay a premier, independent government laboratory like VTT to intentionally destroy your expensive prototype cell at temperatures it was never rated to endure.
That would be a waste of money.
You sweep it into the disposal bin and figure out a better adhesive for your packaging.
But Donut Lab didn't do that. Their CEO, Marco Letamecki, turned this packaging failure into a public demonstration.
Yeah, a massive PR move.
He released a video specifically framing this new, unplanned test as a safety demonstration.
Because his logic was rooted in comparative chemistry.
How so?
Well, if a traditional liquid lithium-ion battery lost its sealed environment and was exposed to atmospheric air at 100 degrees Celsius, the consequences would be violent.
It would explode, right?
Oh yeah. The liquid solvent, which is highly volatile, would vaporize instantly. If atmospheric moisture entered the breach, those solvents would likely hydrolyze into highly toxic gases.
Like incredibly dangerous stuff.
And because of the extreme heat and the presence of oxygen, it would almost certainly ignite and go into thermal runaway.
But DL2 didn't catch fire.
It didn't.
It didn't explode. It just sat there on the testing bench looking like a wrinkled, deflated silver bag.
Exactly. And so, Donut Lab commissioned VT2 to take this already damaged vacuumless cell and put it through a brutal new protocol.
They doubled down.
They wanted to see exactly what a breached, supposedly solid-state cell would do under extreme electrical stress.
Which brings us to the actual parameters of Report 4.
Right.
I want to emphasize this heavily for everyone listening. This was a damaged cell safety test.
Yes, very important distinction.
Because the battery community had been, clamoring for cycle life data showing how many thousands of times the battery could be charged and discharged gracefully.
Right, standard longevity metrics.
Yeah. And when Report 4 was published, some observers looked at it and said, look, the battery degrades terribly, the tech is a failure.
Which is entirely missing the point.
Exactly. Applying cycle life standards to this test is a fundamental misreading of the data.
It's a massive category error. Standard battery safety testing, like the UNR 136 protocols, generally asks the question, can we break this intact battery?
Right, they drop it from a height.
They subject it to severe vibration, they intentionally overcharge it.
Standard torture tests.
But Report 4 asks a fundamentally different and arguably much harsher question. It asks, after the battery is already broken and the internal chemistry is potentially exposed, is it going to kill someone if we keep using it?
Wow. Okay, let's put that into a real-world scenario for you guys. Imagine a rider on an electric motorcycle. They take a hard fall, the bike slides across the asphalt, and the battery pack casing cracks.
A terrible crash.
Right. And the physical impact breaches the foil pouch of the battery cells inside. But the rider picks the bike up, adrenaline is pumping, and they decide to aggressively ride the motorcycle all the way home at full throttle.
Which people do?
All the time. So the question is, does the battery pack explode between their legs?
That is the exact scenario this test mimics. VTT took this damaged, loose pouch and subjected it to 50 continuous cycles at a 5C rate.
Okay, let's translate 5C rate into physical reality because the numbers here are staggering.
They really are.
So a 1C rate means draining the entire capacity of the battery in 1 hour.
Right?
A 5C rate means pushing or pulling the entire capacity in 1/5 of an hour or 12 minutes.
It's incredibly fast.
In electrical terms, they were pushing 130 amps of continuous current through this damaged cell.
130 amps is not a trivial amount of electricity.
Not at all.
To give you a point of reference, that is comparable to the current draw of a professional household arc welder.
Wait, an arc welder, like for melting steel?
Yes, it is a massive river of electrons that generates immense resistive heat as it forces its way through the battery's internal components.
And VTT didn't use any active cooling during this, right? Like they didn't have liquid coolant pumping around the cell to keep it stable.
No. The physical setup was intentionally hostile. The cell was placed inside a Weiss climate chamber, set to a room temperature of plus 25 degrees Celsius.
Just normal room temp.
Right. It was operating between 0 and 90% state of charge.
Okay.
And it was merely wedged between two passive steel heat sinks.
Just cold blocks of metal.
Exactly. Just absorbing whatever heat the battery threw off.
So we have a loose, wrinkled, damaged pouch cell sitting in a room temperature box, having an arc welder's worth of current shoved through it 50 times in a row.
Yes.
Let's look at the results. Did it explode?
It did not.
Okay.
On the Euchre hazard scale for batteries, which ranges from 0 meaning entirely safe, up to 7, which indicates catastrophic explosion and lethal hazards.
Right. 7 is a bomb.
Exactly. This cell's behavior ranked as a level 2.
Level 2, which means defect and damage, but safe.
Correct. There was no fire, no rupture of the remaining casing, and no venting of lethal explosive gases.
That's pretty wild.
By the strict standards of battery safety testing, taking a breached pouch and cycling it at 130 amps without triggering a thermal event is a highly successful safety outcome.
But while it didn't catch fire, it did degrade significantly.
Oh, yes.
The cell suffered a 54.666% capacity loss.
Over half its capacity.
Right. It dropped from a baseline of 24.689 amp hours down to roughly 11 amp hours. Now, if I lose half my battery capacity, I'm usually pretty upset.
Anyone would be.
So why is the company pointing to this degradation as a positive metric?
Because of the context of the Euchre hazard scale we just talked about. If you puncture a standard liquid lithium-ion pouch cell and immediately run 130 amps through it, the ensuing discussion is not going to be about capacity fade.
What's it going to be about?
The discussion is going to be about evacuating the laboratory and dealing with the fire suppression system.
Oh, right, because it's on fire.
Exactly. The fact that VTT was able to smoothly measure capacity fade at all over 50 cycles is the victory Donut Lab is highlighting.
Okay, I follow the logic there. But the most fascinating part of this VTT report isn't the final number, it's the shape of the capacity loss.
The curve.
Yeah, it wasn't a steady, gradual decline like you'd normally see.
No, the degradation curve is the single most vital piece of diagnostic data we have.
Paint a picture of it for us.
When you chart it out, the capacity was perfectly stable for the first 6 cycles. It held strong.
Like nothing was wrong.
Right. Then, between cycle 12 and cycle 26, it experienced a rapid cliff-edge decline. The capacity just plummeted.
Like it just fell off a table.
But then suddenly it stabilized. The curve completely flattened out at around 50% capacity.
You just stopped degrading.
It just stayed there, stable and functional for the remaining cycles of the test.
That is so weird. And the Coulombic efficiency, which, for those who don't know, is the ratio of the energy you get out of the battery compared to the energy you had to put in to charge it.
Right, the energy efficiency.
Yeah, that mirrored the exact same shape. It dropped from roughly 89% during the initial gentle testing down to 83% and then stabilized around 70% during the extreme 5C phase.
It followed the exact same cliff and plateau pattern.
So strange.
And alongside the electrical data, VTT recorded profound physical changes to the cell.
Right, because it started this 50-cycle test loose and wrinkled from the previous vacuum loss.
Yes, but by the end of the test, the physical thickness of the cell had increased by 17%.
17% thicker.
And the pouch was no longer loose. It was completely firm and taut.
It swelled up. But what about the temperature? I mean, if you push 130 amps through a degraded, swelling battery, the resistance must be skyrocketing, right?
You would think so. But that is what makes the thermal data so compelling. Despite the massive current, the surface temperature of the cell only rose about 15 degrees Celsius.
Wait, really?
Yeah. It went from the ambient 25 degrees to roughly 40 degrees Celsius.
That is an incredibly low heat generation for that kind of extreme stress.
It points to a remarkably low internal DC resistance, even after the cell was heavily damaged.
Interesting.
The cell's architecture remained incredibly efficient at moving electrons and ions, generating very little resistive heat, what engineers refer to as I²R heating.
Okay, so let's synthesize this for a second. VTT took a cell that lost its vacuum at 100 degrees, ran it through 50 brutal cycles at 130 amps.
Yeah.
It didn't catch fire, it only heated up 15 degrees, but it swelled by 17% and lost half its capacity in a weird cliff edge pattern before totally stabilizing.
That is the factual observational reality recorded by VTT.
And this is exactly where the pure science ends and the fierce diagnostic debate begin.
Because VTT is an independent testing laboratory.
Right. They are paid to observe and report. They stated that the pouch was wrinkled, and later it was firm and 17% thicker.
They documented the capacity curve.
But they did not state the physical or chemical mechanism of why those things happened.
Exactly. The laboratory reported the what, but legally and contractually, unless they are commissioned to perform a destructive chemical teardown, they do not report the why.
And that purely observational void birthed a massive scientific debate. The data created more questions than it answered.
3 mutually exclusive hypotheses emerged from the scientific community to explain the physics of what actually happened inside that silver pouch.
Okay, I want to spend significant time unpacking these 3 hypotheses because they represent entirely different physical realities.
And we need to give them equal weight.
Absolutely. Let's start with hypothesis A, which is Donut Lab's own account. The manufacturer's explanation. We can call this the hole in the pouch theory.
It is important to contextualize this. For Donut Lab, specifically their CTO, Piippo, and CEO, Marco Latamecki, this isn't a hypothesis in the way it is for us.
Right, because they built it.
They signed the non-disclosure agreements with their material supplier, CT Coating. They selected the specific adhesive for the edge seams of the pouch. They know the exact chemical recipe inside the cell.
Right. They baked the cake. We're just trying to guess the ingredients by looking at a slice.
Exactly. According to Donut Lab, the mechanism relies on mechanical and thermal stress.
Okay, walk us through it.
So during the 100-degree test, the cell wasn't just sitting in an oven. There was a 2.4 kilogram steel plate pressing down on top of it to simulate pack compression.
That's a decent amount of weight.
Donut Lab asserts that the extreme heat, combined with the mechanical pressure, caused the specific polymer adhesive at the edge seam of the pouch to soften and fail.
Huh. As Latamecki stated on a Finnish forum, the pouch glue never fails 100% at once, but gives way at the weakest point.
So the adhesive softened, and a tiny gap opened up along the seam.
Once that microscopic gap formed, the internal vacuum was compromised.
The pouch became loose, and crucially, atmospheric oxygen and moisture slowly began to enter the cell.
So what happens when air hits the internal components of a solid-state battery?
The active solid materials inside the battery, specifically those nearest to the breach at the edge, begin to oxidize.
Okay, they rust.
Yes. And here is the critical physical mechanism. When these specific solid materials oxidize, they physically expand.
Like they grow in size.
Exactly. This is solid material expansion, akin to how iron physically swells and flakes when it rusts. It is not gas inflation.
And this physical swelling leads us directly to CTO Piippo's geometric argument, right?
Yes, but people pointed out that the 17% swelling recorded by VTT was not a curved bubble. It was a uniform, rectangular thickening of the battery stack.
The cell swelled into a thicker, flat slab.
Which is a very strong mechanical observation. Piippo asked a pointed rhetorical question to the community. If you blow a balloon, does it puff up into a rectangular slab?
Well, no. If you blow up a foil balloon, it curves in the middle, the edges pull in, and it gets pilly and round.
Because gas pressure pushes equally in all directions against a flexible membrane.
Right, it seeks a spherical shape.
Precisely. Piippo's argument is that if gas were filling a sealed pouch, the flexible aluminum laminate would bow outward. The fact that the cell remained a flat, rectangular slab indicates that the solid stack of electrodes inside was literally growing thicker layer by layer due to oxidation, uniformly pushing the pouch walls straight out.
Okay, and hypothesis A also perfectly explains the degradation curve, doesn't it? Remember that 50% capacity plateau?
Yes, the capacity curve matches a slow ingress mechanism perfectly.
Ah.
Think of the battery as a thick book.
Okay.
The exposed half of the cell near the edge breach oxidized and degraded rapidly as the atmospheric exposure slowly moved inward, page by page, over those first 26 cycles.
That explains the cliff edge drop.
But eventually the oxidation front stopped. Either it couldn't penetrate deeper, or the oxidized material itself formed a scab that sealed the breach.
Leaving the remaining 50% of the battery, the inner core, perfectly protected from the atmosphere.
Exactly. That protected inner half continued operating flawlessly, which is why the capacity flatlined at exactly 50% and stayed there.
It's like a bruised apple. Half of the apple gets exposed and turns mushy, but if you slice that half away, the remaining core is perfectly crisp and unaffected.
A very apt analogy for solid-state degradation.
Okay, so that is hypothesis A, the manufacturer's explanation. A small hole allowed air in, causing the solid materials to rust, expand into a thicker slab, and kill half the battery while leaving the rest intact.
Right.
Now let's pivot to hypothesis B, because there's a totally different way to look at this same physical data.
Oh, absolutely.
This one comes from Dr. Juho Heiska, an R&D manager and highly vocal external expert. And Dr. Heiska argues the complete opposite physical reality. He argues the pouch never failed at all.
He believes it remained perfectly sealed.
Right.
Dr. Heiska's counterargument is deeply rooted in traditional established lithium-ion battery mechanics. His logic centers entirely on the physical state of the pouch post-test.
Okay, let's look at that.
VTT explicitly reported that the pouch became 17% thicker and, crucially, that it was firm.
Right. The Finnish word used was pinky, meaning pot or pressurized.
Yes. Dr. Heiska argues that a firm, swollen pouch proves unequivocally that the cell is gas-tight.
Because if it wasn't...
His logic is straightforward. If there were a hole, as Donut Lab claims, any internal pressure would simply vent into the atmosphere. The pouch wouldn't become firm and taut, it would remain loose.
Okay, that makes logical sense. But if the pouch is perfectly sealed, what caused the vacuum to disappear and what caused it to swell by 17%?
Dr. Heiska posits that the extreme 100-degree heat caused the internal components of the battery to chemically decompose.
Specifically, he points to liquid electrolytes or the solid electrolyte interphase layers.
Yes.
Wait, before we go further, for anyone who isn't a battery chemist, what is a solid electrolyte interphase layer? Is it like a scab?
That's actually a perfect way to visualize it. The SEI layer is a microscopic protective film that forms on the anode of a battery during its very first charge. It protects the electrode from constantly reacting with the electrolyte. But under extreme heat, this protective scab can chemically break down. When it, or a liquid electrolyte, decomposes, it generates massive amounts of gas.
So Heiska is arguing that the heat boiled the internal liquids or melted the SEI scab, generating a cloud of gas.
Right.
And that gas pressure built up inside the perfectly sealed pouch, expanding it by 17% and pushing the foil walls out until they were taut.
Exactly. And this leads to his most explosive claim.
Which is?
If the cell generates massive amounts of gas from thermal decomposition, it strongly implies the presence of volatile organic liquids. Dr. Heiska went on record stating that, therefore, the solid-state claim is, in his translated words, a marketing department fantasy.
Wow.
His foundational argument is, if it acts like a liquid battery failing, it must be a liquid battery.
That is a direct challenge to the fundamental architecture of the technology. Let me make sure I'm holding both of these in my head.
It's a lot to balance.
Yeah, so Heiska is saying the cell boiled inside its wrapper, created gas, puffed up, and because it stayed puffed up, there can't be a hole.
Right.
Piippo is saying a hole let air in, the solid brick grew, and the growing brick stretched the wrapper tight.
Yes.
Both mechanisms result in a firm, thicker pouch, but the physics are completely opposed.
Which is what makes this diagnostic landscape so murky. Both are valid mechanical theories in a vacuum.
Which brings us to hypothesis C, a middle ground proposed by Ryan Enos Hughes, director of a company called Zeroth.
Yeah, this is an interesting one.
Ryan agrees with Heiska that gas was produced, but he introduces a different mechanism for the degradation, delamination.
Ryan hypothesizes that, as gas was generated inside the cell, perhaps from the intense 5C cycling rather than just the initial heat, that gas forcefully pushed its way between the microscopically thin electrode layers.
Like blowing air between the pages of a closed book.
Exactly. When gas forces those internal layers to separate, they lose physical electrical contact with each other. This is called delamination. When the layers separate, the ions can no longer pass through, and that entire portion of the battery effectively dies, explaining the massive capacity drop.
But wait, how does Ryan explain Piippo's geometric argument, the balloon versus the slab? If gas is building up, why didn't the pouch turn into a rounded balloon?
Well, Ryan provided academic backing for his theory. He cited a peer-reviewed paper titled Gas-Induced Bulging in Pouch Cell Batteries, a mechanical model.
What does the paper say?
This paper demonstrates mathematically that if an internal cell stack is mechanically stiff enough, measured by an engineering metric called a high gamma parameter, the gas buildup can actually be forced to produce a flat-topped rectangular bulge rather than a curved balloon.
Oh, really?
Yes, the sheer rigidity of the internal stack acts like a corset, forcing the gas pressure to spread evenly across a flat plane.
Okay, so a highly stiff internal stack can produce a rectangular bulge from gas. It's rare, but scientifically documented.
It is.
But Donut Lab's CTO, Piippo, had a devastating counter-rebuttal to this delamination theory, didn't he?
He did, and it is an argument based on the path of least resistance.
Okay.
People pointed out a crucial chronological fact. Before the brutal 5C cycling test even started, the pouch was already loose and wrinkled from the 100-degree accident.
The vacuum was already gone. There was empty slack in the wrapper.
Right.
And here is where I think an analogy helps. Imagine putting a deflated rubber inner tube inside a heavy iron safe and then pumping compressed air into the room.
Okay, I see where this is going.
The air is going to completely inflate the loose inner tube way before it ever generates enough force to start warping the iron walls of the safe. Gas will always take the path of least resistance.
That is precisely Piippo's counter-argument.
If gas was suddenly building up inside the cell during the 5C cycling, why wouldn't that gas first inflate the loose, wrinkly outer pouch?
Why would the gas aggressively force its way between tightly packed, heavily compressed, solid internal layers, causing delamination, when there was literally empty slack in the wrapper right next to it?
It totally defies the basic physics of pressure. The delamination theory requires the gas to do the hardest possible work first, rather than just filling the empty space.
Exactly. And that brings us to an independent analysis that heavily tips the scales. An engineer who goes by 2-Bit Da Vinci did a comprehensive forensic analysis of the VTT data.
And he brought up a chemical reality that we haven't touched on yet, which strongly supports Hypothesis A.
Yes, air stability.
This is where the chemistry gets really fascinating. Walk us through the air stability argument, because this seems to debunk the idea of hidden liquid electrolytes entirely.
Well, the timeline of the VTT testing is critical here. This broken, vacuumless pouch sat in ambient laboratory air for hours, days, or possibly even weeks between the various tests.
It was exposed to ambient humidity and atmospheric oxygen.
Right.
So if this cell contained traditional liquid electrolytes, as Dr. Heiska suggested, what would have happened when that room air hit it?
Traditional liquid electrolytes rely on complex organic solvents and lithium salts, like lithium hexafluorophosphate.
Okay, big words, but what do they do?
If atmospheric moisture enters a breach and touches those chemicals, they rapidly hydrolyze. The reaction produces hydrofluoric acid.
Wait, hydrofluoric acid, that eats through almost anything.
Exactly. It would eat through the battery from the inside out.
It would completely destroy the internal architecture of the cell.
The battery would be dead on arrival for the next test. Furthermore, let's say it wasn't a liquid, but it was a sulfide-based, solid-state electrolyte.
Okay, what happens then?
Sulfides are very common in cutting-edge battery R&D right now, but sulfide electrolytes are incredibly reactive to moisture. The moment ambient humidity touches them, the water molecules rip the sulfur atoms out of the crystalline lattice, instantly bonding to create hydrogen sulfide gas.
Hydrogen sulfide, that's the gas that smells like rotten eggs and is highly toxic.
Highly toxic and highly corrosive, but none of that happened.
VTT didn't report hydrofluoric acid.
No.
They didn't evacuate the lab for hydrogen sulfide gas.
No, they didn't.
The damaged cell just sat there on the bench and then happily delivered 24 amp hours of energy at a 1C rate before the extreme 5C cycling even began.
Exactly. So because it didn't dissolve into acid or vent poison gas, the chemistry inside this pouch must be fundamentally, inherently air stable.
Which points massively away from volatile liquids or unstable sulfides.
2-Bit Da Vinci concludes that whatever proprietary composite Donut Lab is using, its air stability is a massive proof point for their claims.
But he didn't stop there. He tackled the 17% swelling head-on. If it's not gas, what caused the swelling?
Right. He offered 4 completely non-gas mechanisms that are well-documented signatures of solid-state batteries.
Let's break these down because this is the real forensic meat of the debate.
The first and most dominant factor is contact loss.
Contact loss.
Yeah. In a true solid-state battery, the solid electrolyte only conducts ions where it is physically touching the solid electrodes.
Because there's no liquid to bridge the gaps.
Exactly. Therefore, solid-state batteries rely on massive mechanical pressure, sometimes tons of applied pressure, to keep those solid microscopic layers mashed intimately together.
And the moment the vacuum was lost at 100 degrees, that essential mechanical compression vanished.
Poof, gone. Without the vacuum compression pulling the pouch tight like a corset, the internal layers were vulnerable.
So what happens when you run 130 amps through it?
When VTT applied that extreme mechanical stress of 5C cycling, shoving 130 amps back and forth, the solid layers began to microfracture and physically pull apart.
Oh, I see.
Every microscopic gap that forms is a dead void. The ions cannot jump across empty space.
And why is this so indicative of solid-state tech? Wouldn't a liquid battery suffer the same contact loss?
No, because a liquid battery is fluid.
Oh, right.
If a microscopic gap forms between layers in a liquid battery, the liquid electrolyte simply flows into the gap. Capillary action pulls the fluid in, and it self-heals the electrical contact.
That makes total sense. Solid-state batteries cannot self-heal a physical void. Once a microscopic gap forms in a ceramic lattice, it is permanent.
And crucially, 2-bit Da Vinci pointed out that this specific degradation signature, a rapid cliff-edge decline followed by a flat plateau, is incredibly well documented in solid-state battery literature.
He brought receipts.
Oh, yeah. He cited peer-reviewed papers from Nature Energy and Science Advances showing this exact curve resulting from contact loss.
Okay, so contact loss explains the degradation curve beautifully. What was the second mechanism?
The second mechanism for the swelling is electrode expansion.
How does that work?
When you violently shove massive amounts of carrier ions into the crystal structure of the electrodes at 130 amps, the host materials physically swell to accommodate them.
Like stuffing too many people into an elevator.
Right. And without the vacuum holding them tight, some of that swelling becomes permanent plastic deformation on each cycle. The solid brick literally ratchets thicker and thicker.
Wow. Okay, the third mechanism he proposed absolutely blew my mind. Because it hinges on the specific metal used in the battery, it involves atmospheric reactions.
This is a brilliant piece of deductive chemistry. As we discussed, a breach allows atmospheric moisture and carbon dioxide into the cell.
Right.
These gases react with the internal alkali metals to form carbonates. Now, if this were a traditional lithium-based cell, lithium carbonate is actually 35% physically larger than pure lithium metal.
So the rusting process would cause massive internal swelling.
Exactly, but the broader battery community heavily suspects that Donut Lab's cell is a sodium-ion battery, not a lithium-ion battery.
Okay, and here's the chemical twist. Sodium carbonate is actually 12% smaller than sodium metal. Sodium atoms pack more efficiently when they form a carbonate.
Right, so if atmospheric rusting was the primary cause of the swelling in a sodium cell, the battery would actually contract slightly, not swell by 17%.
Therefore, the 17% swelling must be primarily driven by the mechanical factors, the contact loss and the plastic electrode expansion, not just chemical rusting.
Exactly. And the fourth mechanism 2-bit Da Vinci listed was simply mechanical fatigue.
Which just makes intuitive sense. You push an arc welder's current through a rigid ceramic matrix 50 times, things are going to microcrack, loosen up, and basically just take up more physical space.
All four of these mechanisms point away from gas and strongly towards solid-state physical expansion.
But 2-bit Da Vinci highlighted one final anomaly in the VTT data, and for many electrochemists, this is the ultimate fingerprint. It is the cycle 56 anomaly.
Yes.
Let's set the scene for cycle 56. So VTT had just finished the 50 brutal cycles at 130 amps. The battery was battered, swollen, and sitting at about 11 amp hours of capacity.
Barely hanging on.
Then they decided to run one final gentle cycle at a 1C rate, just a slow, steady discharge over an hour.
And on that first channel cycle, the capacity of the battery suddenly jumped by a massive 14%.
Wait, it recovered energy that seemed lost?
It did.
How is that even possible? A dead battery doesn't just spontaneously heal itself.
To understand this, we have to go back to the difference between swimming ions and hopping ions that we talked about earlier.
Okay, refresh our memories.
In a liquid battery, ions move through the fluid via diffusion. It is like putting a drop of food coloring in a swimming pool. The color spreads out and equalizes very quickly. Concentration gradients resolve in minutes.
Right, it mixes easily.
But in a solid-state ceramic lattice, ions cannot swim. They must slowly hop from one crystalline vacancy to another. It is a tortuous path, like navigating a massive maze of stepping stones. It takes immense time.
Oh, so during the brutal 5C cycling, they were shoving ions into the maze so fast that they got jammed up?
Exactly, like a massive traffic jam. The extreme current shoved the ions into the lattice far faster than they could evenly distribute.
Okay.
This trapped a massive concentration gradients deep inside the rigid structure. The battery appeared dead because the surface was choked with ions, while the deeper layers were actually empty.
But then during that slow, gentle 1C cycle,
The slow cycle gave those trapped ions the time they needed to slowly hop back into place, deeper into the lattice. The solid ceramic structure finally relaxed.
wow.
This sluggish kinetic relaxation, revealing deeply trapped capacity, is a massive, undeniable fingerprint for a solid-state architecture.
Because a liquid battery would have diffused that gradient in minutes.
Exactly. The fact that it took a slow, hour-long cycle to relax the lattice proves the ions were fighting through a solid.
Let's summarize where we are, because the cognitive load of these three hypotheses is pretty heavy.
It's a lot of chemistry to digest.
Yeah. So hypothesis A says a hole opened, air rusted the solid layers, and the solid brick swelled, choking off half the battery.
Right.
Hypothesis B says the pouch was perfectly sealed, the inside boiled, and gas pressure pumped it up like a tire.
Yep.
Hypothesis C says gas forced the internal layers apart, killing the electrical contact.
And the independent analysis strongly favors hypothesis A, pointing to air stability, contact loss, and the sluggish kinetic recovery of cycle 56 as overwhelming evidence of a true solid-state chemistry behaving exactly as solid-state chemistry should under extreme abuse.
Okay, so we have spent half an hour dissecting the internal physics and chemistry of a damaged battery. But I want to shift gears because this debate isn't actually just about chemistry anymore.
No, it's grown way beyond that.
It has morphed into something much larger. It brings us to the social and philosophical dynamics of the debate itself, what we can call the epistemological asymmetry.
Epistemology is the philosophical study of knowledge. How do we know what we claim to know?
Right.
And when we transition from the physical debate to the philosophical one, we have to ask a foundational question. In a high-stakes technological dispute, who gets to define the absolute truth about an object that only one party actually built?
Let's outline the three tiers of knowledge in this saga, because they are absolutely not equal. At the very top, Tier 1, we have Donut Lab and their upstream manufacturing partner, CT Coding. They hold the absolute truth of the object.
They do. They signed the legal non-disclosure agreements.
Yeah.
They selected the specific polymer adhesive for the pouch edge. They chose the proprietary polymer ceramic composite for the solid electrolyte.
They know exactly, down to the atomic level, what materials were layered into that cell.
Yes.
Tier 2 is VTT, the independent testing laboratory in Finland. They hold observational knowledge.
Right. VTT has the physical cell in their climate chambers. They hook up the sensors, they record the voltage, the current, the ambient temperature, the physical swelling.
But as we established, unless they are commissioned to physically cut the battery open and run a chemical teardown, they do not state the internal mechanism. They report the symptoms, not the disease.
Exactly. And then there is Tier 3, external experts. This includes Dr. Heiska, the thousands of forum commenters, the YouTube analysts, and frankly, us.
Yeah, us too.
Tier 3 operates entirely on inferred knowledge. We are applying generalized textbook chemistry and electrochemistry to a proprietary black box object that we have never physically touched.
And this leads to a dangerous category confusion in the public skepticism surrounding Donut Lab. I want to carefully distinguish between two types of skepticism for you, the listener, because blurring them is causing chaos in the industry. Let's call them Type 1 and Type 2 skepticism.
Okay, so Type 1 skepticism asks questions like, are the performance specs inflated?
Right. And Type 1 skepticism is not just healthy, it is necessary for scientific progress.
Absolutely.
Donut Lab has claimed an astonishing 100,000 cycle life for these batteries. They claim extreme cold weather performance. Those specific world-beating claims have not yet been independently verified by public VTT data.
So demanding rigorous proof for those specific performance metrics before handing over your money is standard, data-driven scientific skepticism.
But Type 2 skepticism is what we saw with Dr. Heiska's quote. Is it even solid state? He called the entire foundational technology a marketing department fantasy.
Which is a huge leap. Type 2 skepticism is a completely different category. This is an extraordinary accusation of fraud.
Yeah, it implies that the manufacturer, the engineers who physically assembled the cell, are either entirely ignorant of the materials they purchased and utilized, or they're executing a massive, coordinated, malicious lie to the public and to investors.
Right. To use a car analogy, Type 1 skepticism is saying, I don't believe your new car can actually go 200 miles an hour. Show me the track data.
Right, prove it.
But Type 2 skepticism is saying, I don't believe your car even has an engine. I think it's just pedals under the floorboards and you're lying to everyone.
That is a very clear distinction. And this brings us to a phenomenon we can call the reversibility asymmetry, which explores the social and psychological dynamics of this debate.
That is fascinating.
In the tech and science world, skepticism is almost always viewed as the safe social position. You look smart, analytical, and rigorous when you doubt things. Nobody wants to be the gullible fool who bought the snake oil.
Right. But there is a psychological trap hidden in that safety. If you take a type 1 position and say publicly, I doubt the 100,000 psych spec, you can easily change your mind when new VTT data arrives without losing face.
You just say, the new data convinced me, science works.
Exactly. But if you publicly declare the technology a marketing fantasy, if you take that extreme type 2 position, you have burned your bridges.
You're all in.
You cannot walk that back without severe reputational damage. You have staked your professional credibility on the direct accusation that specific engineers at Donut Lab are lying.
And this triggers well-documented psychological phenomena, belief perseverance, and the backfire effect. Can you explain the backfire effect in this context?
Well, when a human being publicly commits to a strong identity-linked position, and then they are presented with objective evidence that contradicts that position, they do not naturally update their views.
Because the cognitive dissonance is too painful.
Exactly. Instead, the backfire effect causes them to double down on their original belief, often aggressively.
So, as more data emerges that is highly consistent with a solid-state chemistry, like the miraculous air stability or the contact loss degradation curve or the cycle 56 kinetic recovery, the people who loudly committed to the fraud narrative will fight that data even harder.
Because accepting the data means admitting they made a false, defamatory public accusation. The debate stops being about the electrochemical properties of a battery in Finland and becomes a desperate attempt to protect the skeptic's identity as the smart person who saw through the scam.
Man, to provide some external balance to this psychological deep dive, we really need to bring in Dr. McTurk. He hosts the Everything Electric show, and he is a credentialed electrochemist with absolutely no stake in this fight.
And he looked at the VTT data and pointed out a vital, undeniable fact regarding the initial 100-degree vacuum loss event.
Right. Dr. McTurk provided crucial external validation. He noted that a vacuum loss at plus 100 degrees Celsius with zero resulting fire is fundamentally, unequivocally consistent with a solid-state architecture.
As we discussed earlier, a traditional liquid chemistry packed with volatile organic solvents would have violently reacted the moment it met atmospheric oxygen at those temperatures.
It would have burned down the lab.
Yes. The mere survival of the cell on the bench is, in itself, profound evidence of a novel chemistry.
Okay, I have to play devil's advocate here because we've been very hard on the skeptics. I need to push back. Manufacturers can lie. They do lie.
That's true.
Theranos is the ultimate lingering cautionary tale of the 21st century. Elizabeth Holmes lied to investors, she lied to doctors, she lied to patients about a medical diagnostic device. Why shouldn't the battery community assume the worst when a startup makes impossible-sounding claims? What makes the structural conditions here any different from Theranos?
It is a vital question, and the Theranos comparison is the default reflex for anyone analyzing hardware startups. But if we look closely, the structural conditions here are radically different.
Okay, how so?
First, Theranos relied entirely on secret, proprietary testing in their own locked laboratories, hiding behind a charismatic solo founder. Donut Lab is using VTT, an independent, government-backed laboratory with rigorous European standards.
Right.
VTT has its own massive institutional reputation to protect. They are not going to falsify data to help a motorcycle startup.
That is a massive difference. External, uncontrolled validation.
Second, we see the mule bike demonstration. Donut Lab actually integrated the technology into a physical prototype motorcycle and demonstrated pack-level fast charging at a public Circle K station in the freezing cold.
In public.
Right. Theranos never allowed their machines to be independently operated in the wild by third parties. And third, Donut Lab is tied to the upcoming Verge electric motorcycle delivery timeline.
Oh, right, the actual product launch.
There are massive, imminent reputational and financial risks. You can fake lab data for a few months, but you cannot fake a commercial motorcycle failing on the highway when thousands of customers receive it. The structural incentives for a total foundational lie simply do not align with their highly public actions.
Okay, that makes sense. It's a completely different game board with much higher transparency. But this brings us to the path of resolution, because we just spent the better part of an hour debating complex electrochemical hypotheses, the psychology of belief perseverance, and corporate strategy.
We covered a lot of ground.
We really did. But this entire philosophical and scientific debate could literally be ended in a single afternoon.
It could. The answer isn't theoretical. It is a physical reality locked inside a silver pouch.
There is a definitive, well-established test that could discriminate instantly between Donut Lab's Hypothesis A and Dr. Heiska's Hypothesis B. It is called gas composition analysis.
Yes.
Walk us through exactly how that test works.
You take the contested DL2 pouch cell. You place it inside a highly controlled sealed environment chamber. You mechanically puncture the pouch, and you run the interior atmosphere of the cell through a mass spectrometer.
And a mass spectrometer is a device that identifies the exact chemical makeup of a gas by ionizing the molecules and sorting them by mass.
Precisely.
And the outcomes of this test are entirely binary. It would instantly prove who is right.
Completely. If the mass spectrometer detects high levels of ambient nitrogen, oxygen, and subsequent solid oxidation products, it proves atmospheric ingress. Donut Lab is telling the truth. There was a hole and air got in.
And if they find something else?
If the spectrometer detects organic solvent vapors like vaporized carbonates or ethers, it proves liquid electrolyte decomposition. Dr. Heiska and the skeptics are right.
It really is that simple. One test. And what about Hypothesis C, the delamination theory? How do we prove or disprove that?
Cross-section imaging. You take the cell, you physically cut it open, or you put it through a high-resolution CT scan.
Just look inside.
Right. If you see the microscopic layers physically separated with gas pockets ballooning between them, the delamination theory is correct.
And if not?
If the layers are physically intact and tightly packed, but visibly rusted and oxidized on one side, Donut Lab is correct.
So if the tests are this simple, who has the power to run them? Who actually holds the battery?
VTT. According to VTT's standard contract terms, specifically Section 6.3, the tested cell remains the legal property of the client, Donut Lab.
Okay.
However, VTT still physically has the cell unless it was shipped back. And crucially, under Section 8.4 of VTT's general terms, the laboratory retains the legal right to disclose information to verify or rectify claims or statements made by a client in the public domain.
That is a massive contractual clause.
It is. If Donut Lab is out there lying about the VTT data or twisting it to hide a liquid battery, VTT has the explicit legal right to step up to a microphone and say, actually, no, that is false.
Exactly. To pursue this resolution, we actually formally reached out to VTT researchers Ari Hentunen and Mikko Pallotti on March 24, 2026.
We did.
We asked for direct scientific clarification on the vacuum loss mechanism, citing the intense public debate and invoking Section 8.4.
And what does they say? Did they clarify if it was a hole or gas pressure?
As of the production of this deep dive, there has been absolutely no response. Total silence.
Which leaves the community spinning its wheels in the mud. And this leads to a necessary critique of Donut Lab's PR strategy.
Because why do they withhold basic specifications, things like the physical weight of the cell or the low-temperature performance data? Disclosing the weight of the battery wouldn't violate their non-disclosure agreement with CT coding?
Not at all. It doesn't reveal the recipe. It's just a number on a scale.
Right.
This is what marketing analysts call the drip-feed marketing trap. And based on the evidence, it appears to be an entirely deliberate strategy by Donut Lab.
How so?
If we look back at the very first I Don't Believe video, CEO Marco Litthamecki explicitly outlined this strategy. He stated that they actively want loud voices in the industry to go on record saying this technology is impossible before they drop the definitive evidence.
Oh, wow. They are using the withheld metrics as bait.
They are deliberately inviting type 2 skepticism. They want established experts to scream fraud so that when the final undeniable validation arrives, perhaps when the motorcycles actually ship, the paradigm shift is highly publicized and the skeptics are publicly humiliated.
It is a combative, high-wire PR strategy.
Extremely.
But is it actually working? Or is it backfiring on them?
Well, by tracking community sentiment algorithms across EV forums, LinkedIn discussions, and video comments, we know this strategy is causing massive self-inflicted credibility damage to Donut Lab.
Really?
Positive sentiment dropped from 35% to 20% in a single week following Report 4. Frustration is rising exponentially. The drip feed of data is exhausting the community. Donut Lab is confusing a viral marketing campaign with a rigorous scientific peer review process, and the audience is simply losing patience.
It is a dangerous game to play with your own reputation, treating scientific validation like a reality TV reveal.
It definitely is.
As we wrap up this deep dive, I want to ask you, the listener, to consider the moral burden of analysis here. If an independent analyst looks at the VTT data, they see the contact loss degradation curves, they see the incredible air stability, they see the cycle 56 kinetic recovery.
Which is huge.
Right, and they conclude, based on the laws of physics, this looks exactly like a solid-state battery. They are doing good science.
They are evaluating the available evidence objectively without malice or bias.
Right. And if Donut Lab later turns out to be a massive, coordinated Theranos-level fraud that somehow fooled everyone, the moral burden falls entirely on the scammers who fabricated the data.
Absolutely.
The moral burden does not fall on the analyst who followed the evidence in good faith. You shouldn't be afraid to analyze data just because you are terrified of looking foolish on the internet later. The data is the data.
The standard of scientific inquiry is whether you follow the evidence reasonably with the information available to you at the time. It is not about perfectly predicting the future.
Exactly. So let's summarize the open state of this investigation. Every VTT report we've looked at so far has advanced our understanding incrementally. Report 4 is no different.
No, it didn't change everything overnight.
It didn't rupture the narrative. It just provided one more vital, extreme data point in a very long series.
It confirmed that the cell can survive extreme thermal and electrical abuse without catastrophic failure. But it left the mechanical reality of that abuse open to interpretation. The debate remains completely open.
And we have not declared a winner today because both sides have laid out highly specific, chemically valid arguments based on the limited information they have.
Exactly.
And that leads to a final provocative thought I want to leave you with. We just spent a massive amount of time debating complex electrochemical hypotheses, the psychology of belief perseverance, and the risks of Silicon Valley marketing strategies.
A lot of theory.
But the answer to this entire mystery isn't theoretical. It isn't philosophical. It is a physical object.
The contested cell, DL2, is currently sitting on a shelf or in a storage bin in a government laboratory in Espoo, Finland.
3 hypotheses, 1 simple gas analysis test. The X-ray machine isn't broken, we just haven't turned it on yet. The evidence exists. The only remaining question is whether anyone will actually look at it. Thank you for joining us on this deep dive. Be sure to check the show notes for the source teardowns and the raw VTT data. We'll see you next time.